Great. So we're very happy to have Andrea to talk about asymptotic symmetries and celestial CFT. Please go ahead.
Thanks a lot for the invitation to speak, and many thanks to Jeff and all the other organizers for making this event possible virtually. It would have been a great pleasure, of course, to be in Cape Town physically for both Strings 2020 and Ropes 2020. But it is a great consolidation prize to have this event come online, which has allowed so many more participants to come together. So my talk will be in the context of recent attempts at flat space holography, with focus on the asymptotic symmetries of asymptotically flat space and how they manifest themselves in a proposed dual celestial CFT. The results that I'm going to present will be largely based on a paper that came out in May, which were done in collaboration with Laura Donnet, who is a postdoc at TU Vienna, and Sabrina Bastersky, who is a postdoc in Princeton. It will also build on earlier work, including a paper with Laura and Andy Strominger from a little over 2 years ago, which has brought me to this topic. So I think it is fair to say that most of our recent understanding of quantum gravity comes from the holographic principle applied to enter de Sitter space, where the gravitational and stringy bulk physics has a dual description in terms of a conformal field theory living at the boundary of enter de Sitter space. Underlying this powerful duality is the identification of the symmetries of enter de Sitter space with those of a proposed holographic dual boundary theory, and the match of the degrees of freedom, which is beautifully exemplified by the explanation of the black hole entropy from the dual CFT. Now, one of the distinguishing features of enter de Sitter space is, of course, its confining boundary conditions, which lead to the slogan that we can study quantum gravity in a box. Now, the spacetime near highly charged or highly rotating black holes is well described by enter de Sitter space, but vast regions of our universe are not. So at the cosmological scales, we should, for example, rather use de Sitter space, while there are many scales in between for which Minkowski space is a good approximation, at least away from sources. So this begs the question how generally applicable the holographic principle is. And in particular, can the four-dimensional space-time physics in asymptotically flat space be encoded in some dual boundary theory that lives perhaps at the conformal boundary of Minkowski space? Now, any attempt at such a flat space holography has to answer a set of fundamental questions, and some of these include: what are the symmetries of the space-time? Can they be identified with those of a dual boundary theory? Is this dual boundary theory a conformal field theory? What are its properties? And so on. Related to this set of questions is the realization that there exists a conformal basis for quantum field theory scattering amplitudes. And this arises because the four-dimensional Lorentz group acts on the celestial sphere at null infinity as the global conformal group. And this means that four-dimensional scattering amplitudes can be recast in terms of two-dimensional correlation functions. Now, the study of this conformal basis might give us powerful constraints on the quantum gravity S matrix, as well as provide new insights into hidden structures and symmetries of amplitudes. In this talk, I will like to study and discuss a unified treatment of so-called soft modes in this new conformal basis with a view towards flat space holography. In particular, I would like to discuss the spectrum of two-dimensional primaries in this pure-diff celestial CFT. I will discuss the symplectic pairing of so-called conformal primary wave functions, which is important for understanding the soft sector of the theory. And I will give an example of a celestial analog of quantum field theory soft theorems. Now, this discussion feeds into a question that any attempt at flat space holography has to answer. And this question is, what is the asymptotic symmetry group of Einstein gravity at null infinity? This is, of course, an old question, but we will look at it from a new angle, namely from this angle of having a new conformal basis at our disposal. And this will allow us to identify certain gravitational modes in this new basis with the generators of asymptotic symmetries. This consists of the BNS group, as well as a celestial conformal symmetry group. Now, the latter comes in the form of two distinct proposals, one being the Virasoro symmetry group generated by local conformal killing vectors, and the other being a more general diffeomorphism symmetry on the celestial sphere. Now, there are important differences between these two proposals, and there are subtleties, And I will discuss them in the context of this conformal basis, which will shed new light on these subtleties. So the discussion of flat space holography should probably start with the Penrose diagram of Minkowski space. Here are highlighted in blue the conformal boundary of Minkowski space given by null infinity, which is a natural place where a dual boundary theory would live. So this is the place where massless particles enter the spacetime and exit it. Of course, massive particles start out at the bottom here at past time like infinity and end up at the future at the top at future time like infinity. A convenient coordinate system that describes the physics near null infinity, near this conformal boundary, is given by Bondi coordinates. This consists of a radial coordinate r, a set of complex angle coordinates z and z bar, which denote the angles on the two-sphere, and retarded time for parameterizing future null infinity and advanced time v for parameterizing past null infinity. Now in this two-dimensional diagram, I have of course omitted the two-sphere. So this is given by a pair of points, one on the left and one on the right with respect to the origin, which is given by this straight line here. Pushed to infinity, this two-sphere is then the celestial sphere. Now, scattering amplitudes in Minkowski space have to obey Lorentz symmetry, and this acts as the two-dimensional celestial sphere as the global conformal symmetry group. So the four-dimensional S matrix, which is labeled by the energy, the momenta, and the helicities of the external particles, can in this way be recast as a two-dimensional correlation function, where operators are inserted at points z, z bar on the celestial sphere, and are labeled by the quantum numbers under the conformal group, namely the conformal dimension delta and the spin j. Underlying this equivalence is a change from the usual momentum basis that makes translation symmetry manifest to a new basis that makes conformal symmetry manifest. This basis change is achieved by an integral transform called a Mellin transform, which in this context is given by an integral over the energies from 0 to infinity with this factor energy to the power delta minus 1. The momenta get now replaced by the points on the celestial sphere where particles enter and exit, and the helicities under this map get identified with the 2D spin. The notion of energy now gets replaced by the introduction of the conformal dimension delta by this integral transform. Plane waves with energy omega and momentum p, or equivalently null vector q, get now mapped to boost eigenstates, which are given by 1 over the null vector dotted into the spacetime vector to the power delta. A basis of finite energy wave functions is now mapped to a basis of new wave functions. And these wave functions have the property that the conformal dimension lies on the principal continuous series of the Lorentz group. So in order to have a complete delta function normalizable basis, the condition on delta is that its real part has to be 1 and its imaginary part is a real number. Now, the interesting property of these new wave functions is that they transform as conformal primaries under the conformal group with weights h and h bar. The Mellin transform of these plane wave functions gives rise to scalar conformal primaries, while by adding suitable polarization vectors and tensors, we can get wave functions that are gauge equivalent to spin 1 conformal primaries and to spin 2 conformal primaries. So under this map, we have an identification of massless particles with these conformal primary wave functions. Now moving on from wave functions to amplitudes, we can now Mellin transform each of the external particles in an amplitude, and in this way obtain a celestial amplitude, which, as already mentioned, takes the form of a two-dimensional correlator. Now, as an example, let's consider Young-Mills theory and look at the 4 gluon amplitude given on the left. A Mellin transform of each of the 4 external particles will take it to a celestial amplitude, which we recognize as a 4-point correlator in the two-dimensional CFD. Z here is given by the conformal cross ratio, and this universal factor here is given in terms of the distance of points Zi minus Zj on the celestial sphere. Now, what's less familiar in this correlator is the appearance of these delta functions. And this hints at a more exotic nature of this putative celestial CFD. Now, what about the spectrum? So finite energy wave functions get mapped to conformal primary wave functions on the principal continuous series. And this map involves integrating over all the energies. So what is immediately clear from this integral transform is that the notion of an energetically soft particle, namely one where its energy is taken to 0, gets lost in this transform. But this limit is an important limit in quantum field theory scattering amplitudes that tells us about universal factorization properties. And surely universal properties of amplitudes should not be lost under a simple basis change. So something should take its place. So what we proposed was that instead of the conformally soft limit, in this new conformal basis, one should take the conformally soft limit. So this corresponds to taking the weights, h or h bar under the conformal group, to 0. But actually there's a bigger story here, which is that the orders of omega in an energetically soft expansion of the amplitude gets now mapped to poles in the conformal dimension of the corresponding 2D correlator. And the poles arise at certain integer values of the conformal dimension delta. So while, for example, for Yang-Mills theory, the conformally soft limit, which would agree with taking h or h bar to 0, would correspond to taking delta to 1. For these other conformally soft limits, this takes us off the principal continuous series. And this immediately raises a question, namely, how are these conformally soft modes consistent with the statement that conformal primary wave functions on the principal continuous series form a complete basis? Now, this tension is only apparent and can be resolved by studying in more detail the conformal primary wave functions and the Mellin transform and its inverse. And I will do this now for gravity. So we start again with the Mellin transform of a plane wave of spin 2, which is labeled by the conformal dimension delta and the spin. From now on, I will denote the spin by this two-dimensional index A. If it takes the value WW, this corresponds to spin plus 2. And if it is W bar, this corresponds to spin minus 2. The plus minus label here denotes whether the wave is outgoing or incoming and is in correspondence with a plus minus I epsilon prescription of the 0 of this denominator here, which happens along the light sheet. Now this wave functions is not yet a conformal primary, but can be made into one by adding a total derivative term. And this total derivative term is given by this diffeomorphism zeta delta. Now, I would like to emphasize that this diffeomorphism is not just a trivial diffeomorphism that denotes a redundancy of the theory, but actually for the conformally soft limits that we'll be interested in, this corresponds to a large diffeo, a large gauge transformation that changes the physical state at the boundary. So now these objects H delta form a basis of conformal primary wave functions of spin 2 with conformal dimension on the principal continuous series. And now, while I'm at it, let me also introduce another interesting integral transform, which is called the shadow transform, which will be useful in the following. So this is a transform that takes an operator of dimension delta to an operator of dimension 2 minus delta, or delta tilde for short, and flips its spin. Okay, now the statement is that conformal primary wave functions of arbitrary conformal dimension delta, written here on the left, can be obtained from a certain contour integral of principal series wave functions denoted by HS on the right. So in this contour integral, there's this boldface delta denoted in red, and this corresponds to a regulated version of a distribution that is generalized to the complex plane. When the real part of delta lies on the principal series, so on this contour, then this distribution just reduces to the ordinary Dirac delta function, and this equality is just trivial. When the real part of delta lies to the left or to the right of the principal series, then we can use a regulated version of this distribution, which is given by the Mellin transform of an exponential. And that has the well-known result that it's given by the gamma function. And nu here is a regulator that will take to 0 in the end. So now when we plug in this expression into this contour integral, it's immediately clear what we have to do. So we can close the contour either to the left or to the right, depending on where it converges, and then use the residue theorem to pick up the poles of the gamma function. In this way, we will validate the statement that conformal primaries with arbitrary delta can be expressed in terms of principal series wave functions. And so this resolves the tension that the conformally soft limit in the spaces given by certain integer values of delta does not augment the principal series basis, but instead these wave functions can be obtained from a certain superposition of principal series wave functions. Okay, with that understood, it is now natural to expand a general metric perturbation H in this conformal basis purely in terms of principal series wave functions. So these are given in blue here. In red are the creation and annihilation operators, and these curly ends here are normalization factors that give us the canonical commutation relations for A and A dagger. Now I would like to introduce a mode operator Q delta with respect to a suitable inner product, which is denoted by these round brackets here, and evaluate it on some Cauchy slice sigma. This mode operator has the property that it shifts the metric according to this expression. And when acting with it on the vacuum, it produces single particle states with this profile H delta. Now the notation here is not accidental. These modes Q delta will actually correspond to charges. And in particular, when we take the conformal soft limit of taking delta to 1 or to 0, these Qs will correspond to asymptotic soft charges at null infinity once we take this Cauchy slice to null infinity. And this brings me to the discussion of the asymptotic symmetry group, which starts with imposing boundary conditions. So in a radiative spacetime, we have to add to the exactly flat Minkowski metric extra terms, and these extra terms are characterized by the free data. So this is a 1/r expansion, and there are functions of the angles and the retarded or advanced time, and these are given by these three terms. So this is the Bondi mass aspect, the angular momentum aspect, and the gravitational data. And these are related by a constraint equation, but otherwise an arbitrary function of the angles. Of particular importance will be the change of the gravitational data with respect to retarded time. And this expression defines the Bondi-News tensor. So this is in a sense a dynamical graviton mode. Now the asymptotic symmetry group is then defined as the set of allowed gauge transformations that respect the chosen boundary conditions, modded out by the trivial ones. And by trivial ones, I mean gauge transformation that vanish at the boundary and denote the redundancy of the theory. Now, what is the asymptotic symmetry group of asymptotically flat space? Well, the most naive guess is that it should be the Poincaré group. After all, fields grow weak, far away, and the curvatures are low. So what else could it be? But however, what has been found instead was that the translations of the Lorentz group, of the Poincaré group, get instead locally enhanced. And this leads us to the so-called BMS group, which is given by the boundary conditions as written here. So there are order 1/r, order 1, and order r contributions to the metric. And I have explicitly written out the order r contribution to the angular piece of the metric, which is given by the gravitational data. And this will be the key player in the following. So now asking what gauge transformations respect these boundary conditions lands us at the following diffeomorphism vector field zeta. So this is given in terms of a function f, which is an arbitrary function of the angles. The action of this diffeomorphism on the metric, and in particular on the free gravitational data, is given by this expression here, where the blue term highlighted here corresponds to an inhomogeneous shift. For the ZZ component of the gravitational data, this inhomogeneous shift is simply given by two covariant derivatives acting on this function f. The physical effect of this diffeomorphism is now that the global translations get enhanced to angle-dependent super translations that are characterized by this function f. In other words, global energy conservation now becomes a statement that energy is conserved at every angle. And so by allowing for these diffeomorphism vector fields, the Poincaré group gets enhanced to the BMS group. BMS supertranslations are related to other gravitational infrared effects. These are the gravitational displacement memory, which was first studied in the 70s, and Weinberg's soft graviton theorem, which was studied in the mid-60s. Now, I would like, if asymptotically flat space is holographic, then we should be able to describe these effects purely in terms of two-dimensional language. And this is what I want to turn to next. So I already hinted that the conformally soft limit is given by taking the conformal dimension to certain integer values, and these integer values start at 1. In that limit, the conformal primary spin to wave function reduces to a total derivative. And the effect of this diffeomorphism vector field zeta is that it changes the physical state at the boundary. And this change is given in terms of a function f, that's a specific function of the angles, which is denoted here for a positive helicity graviton, as indicated by this WW here. Now we recognize that this physical change of the boundary state corresponds precisely to the effect that a BMS supertranslation has. So this delta equals 1 primary mode corresponds to the Goldstone mode of spontaneously broken BMS symmetry. One can compute a soft charge or define a soft charge for this BMS symmetry. And this is given by this expression in the box, where the blue term corresponds to this inhomogeneous shift, while the red term corresponds to the bond-induce tensor of the background. Now, in this limit of delta going to 1, there is an immediate puzzle that presents itself. And this is as follows. So in the conformal basis, primary wave functions are paired. And in particular, they are paired with respect to some suitable inner product. They are paired between wave functions with dimension 1 plus I lambda and 1 minus I lambda. Now in the limit where lambda goes to 0, or equivalently delta goes to 1, it is not obvious what the symplectic or canonical partner with respect to such an inner product what the symplectic partner for this dimension 1 Goldstone mode should be. And moreover, these shadow primaries that I introduced before, when the dimension of those is also taken to 1, these correspond to total derivative terms as well, and moreover coincide precisely with the dimension 1 Goldstone mode. In the momentum basis, the partner of this Goldstone mode is the soft graviton. And this is obviously important for the soft graviton theorem and for gravitational memory. However, in this new conformal basis, after performing the Mellin transform, it is very subtle to see where this symplectic partner of the dimension 1 Goldstone mode is, or equivalently, what the celestial analog of the soft graviton is. One way to understand where this partner comes from is by realizing that there exists a logarithmic branch of the solution space, which is not captured by the Mellin transform of a plane wave, naively. So this is obtained by taking a combination of primaries with dimension delta and their shadows, taking a derivative with respect to the conformal dimension, and then taking the conformal dimension to 1. So this is a quantity that remains finite in the conformally soft limit, and it does not correspond to a total derivative. So this comes with in and outgoing modes. And when taking a certain combination of in and out modes that does not decouple in scattering amplitudes, we arrive at the new conformal primary, which is the celestial analog of the soft graviton. So this dimension 1 conformally soft graviton is given by this distributional expression, and it can be visualized as a gravitational shock wave that has support along and outside the light cone of the origin. Now one can explicitly check that this new conformally soft graviton mode is the symplectic partner of the dimension 1 Goldstone mode. And so in this sense, we've understood that there is a symplectically paired set of zero modes, where one of the modes is not trivially visible in the conformal basis after performing the Mellin transform. Now, starting from this mode operator that I introduced earlier, we can construct a descendant which has conformal weights 3½ and 1/2. So this is a curious object. And this descendant in the conformally soft limit when delta is taken to 1 turns out to correspond to the BMS supertranslation current. So this is the generator of BMS supertranslation symmetry. Now one can ask what happens when this BMS supertranslation current is inserted into amplitudes. And let me start by discussing the momentum space version, which is Weinberg's soft graviton theorem. So when the energy of an external graviton is taken to 0, then the amplitude factorizes into a lower point amplitude without the graviton and the soft factor that corresponds to a pole in the energy. To project out this pole, we can start from the amplitude, multiply it by the energy of the nth particle, and then take this energy to 0. In this way, we get a factorization of the lower point amplitude and a soft factor. And the soft factor has a dependence on the momenta, or equivalently on the points on the celestial sphere where particles enter and exit. and explicit appearance of this factor of the energy of the kth particle. And then there's a sum over all the n-1 remaining particles. Now, the explicit appearance of this energy here can be understood from the OPE of the operator with that energy and the supertranslation current. So this funny looking OPE with the supertranslation current gives an explicit factor of the energy. And this is very important when trying to understand the celestial analog of soft theorems. So here, instead of the energetically soft limit, we should take the conformal soft limit of delta going to 1. And the first thing to notice is that the explicit appearance of this factor of energy in the OPE with the supertranslation current gets mapped to a shift in the conformal dimension of the operator in the conformal basis. And this means that the conformal soft graviton theorem in this new basis has now the lower point amplitudes has a shift in the kth conformal dimension in the lower point amplitudes. So the momentum space factorization is not exactly mimicked in the conformal basis. Instead, we have a factorization of 2D correlators into a sum over lower point correlators and an explicit conformal soft factor that only depends on the angles. Now, the angular dependence here is precisely the same as that of the soft factor in the momentum basis. And the explicit appearance of the energy of the kth particle in the soft factor on the momentum basis gets now mapped to a shift in the kth conformal dimension of the lower point correlators, which are summed over. Okay, so this is very nice because these two-dimensional correlators are a bit more exotic than the usual ones, but the universal factorization properties in momentum space gets now mapped into a universal conformal soft factorization in this conformal basis. Now, this result is perhaps both expected and surprising. It is expected because universal factorization properties of amplitudes should not be lost under a basis change. But on the other hand, this integral transform was over all the energies and in particular mixes the infrared with the ultraviolet. And so a priori, it was not clear how the energetically soft limit gets mapped to a momentum space, a conformal basis statement. But it's very nice that this universal property has a corresponding version in this conformal basis. Now, having accepted that translations get locally enhanced in asymptotically flat space, an immediate question is whether the Lorentz group doesn't also get locally enhanced. And this leads me to the discussion of the extended BMS group, which was originally conjectured, but has by now, I think, been solidified by various very nice results. So again, we start with a discussion of the boundary conditions. And now the extended BMS group contains a diffeomorphism xi, which rather than depending on a function as in the BMS case, depends now on a vector field. And this vector field, y, is allowed to be singular on the two-sphere. Originally, such a vector field was disallowed. So all the singularities on the two-sphere were disallowed. And so the only thing that was left was the Lorentz group. But if you allow such singular vector fields, you get an enlarged symmetry group. And this corresponds to a diffeomorphism symmetry on the celestial sphere. The effect of this diffeomorphism xi on the metric is again a shift in the gravitational data, which for the ZZ component now takes the form of 3 covariant derivatives acting on this vector field now, and the factor of retarded time, or equivalently advanced time at the other boundary. What's now different to BMS is that also the leading metric gets shifted. So there's an inhomogeneous shift of the celestial sphere metric at leading order. And this will have important consequences when computing the soft charges associated to this symmetry. So physically what this means is that the global rotations and boosts get now enhanced to angle-dependent superrotations, which are characterized by this vector field y. If this vector field is holomorphic, then this diffeomorphism xi gives rise to a Virasoro superrotation symmetry, while if y is an arbitrary vector field on the angles, it gives rise to a more general diffeomorphism symmetry. So in other words, the physical effect of this, of adding these diffeomorphisms is that angular momentum is now conserved at every angle. Now, similarly to the leading case, to a BMS supertranslations, these new Virasoro and Diff superrotations are also related to other infrared gravitational effects, namely the spin memory effect, which is subleading to the gravitational displacement memory, and a subleading soft graviton. And unlike the leading cases, these effects were only found very recently. Now, let me zoom in a bit more on this relation between the water density of asymptotic symmetries and the subleading soft graviton theorem. So what was shown is that the subleading soft graviton theorem implies a water density for Virasoro symmetry when this vector field Y is holomorphic. Unfortunately, it appears that this relation is not bijective. And this has led people to suggest that perhaps we should extend the Virasoro symmetry group to all of diffeomorphism symmetry. So this means that the vector field Y should be allowed to be not only holomorphic, but any function on the celestial sphere. And what was found here was that the water density for this symmetry group is actually equivalent with the subleading soft graviton theorem. However, the price to pay for this nice equivalence is that the phase space has to be enlarged. And the reason for that is that these diffeomorphisms change the metric on the celestial sphere at leading order. Now, what we'll find in a little bit is that when taking the perspective of this celestial CFD or take the perspective of this conformal basis, we will find that particular vector fields Y are related between the Virasoro symmetry group and the Diff2 symmetry group. And in that sense, we can connect these two asymptotic symmetry groups and discuss in a bit more detail their differences and similarities. Now, in addition to the dimension 1 Goldstone mode, which gave rise to BMS symmetry, in this conformal basis, there are two more pure diffeomorphisms. There is one that arises when the dimension of the primary is taken to 0, and another one that is obtained when the shadow dimension of the shadow primary is taken to 2. Now for this shadow primary of dimension 2, we have a diffeomorphism Xi2, which at the boundary gives rise to a shift in the physical state, which is given by this expression, where this vector field YZ is a holomorphic function 1 over Z minus W, which I gave here for a positive helicity graviton, as denoted by WW. Now, we will find that the conserved soft charge that is associated to this diffeomorphism symmetry is actually the two-dimensional stress tensor for 4D gravity. So this has weights 2,0 for a positive helicity graviton. And the stress tensor is the generator of this Virasoro superrotation symmetry for holomorphic vector fields Y. On the other hand, for this dimension 0 Goldstone mode, we have a vector field that's non-meromorphic. And it turns out that the conserved charge with respect to this symmetry is actually the shadow transformation of this 2D stress tensor. So this has weights minus 1,1, and it is the generator of a particular diffeomorphism symmetry, namely for this vector field, which for obvious reason we have denoted by a shadow superrotation symmetry. Now, the way I'm introducing this, it might seem rather natural that the conserved charges with respect to the symmetries should correspond to the stress tensor and its shadow. But from the asymptotic symmetry point of view, this is not at all obvious. In particular, since it was argued that the diffeomorphism group will give rise to radially divergent surface charges. And there's this issue about having to enlarge the phase space. So let me discuss these subtleties in a bit more detail and tell you how one obtains these soft charges being the stress tensor and its shadow. So this starts with the covariant phase space formalism and the computation of the Ayerwald symplectic structure. So this is done around a fixed background G for two variations, one of which will be taken to be either of these two Goldstone modes, H0 or H tilde 2. So now the subtlety is the following. This diffeomorphism symmetry shifts the metric at leading order. So this is the celestial sphere metric that is changed at leading order. For the shadow dimension 2 primary, this shift is just a contact term. And previously in the literature, such contact terms have been dropped, which makes it look like that these two symmetry generators are actually on different footing. But what we'll do here instead is keep track carefully of all the contact terms. And this will show us that these two modes, which correspond to a Virasoro symmetry and Diff-2 symmetry, are actually on equal footing, at least as far as the computation of the soft charges is concerned. Okay, so this shift at leading order in the celestial sphere metric, what this does is it leads to a radially divergent symplectic structure. But fortunately, there exists a way to relomanize that, which was discussed in this paper. So what happens is that in the covariant phase space formalism, there is an ambiguity for adding boundary terms. And fortunately, the radial diversion that appears here is such a boundary term. And so we can subtract it. So after doing that, we obtain a renormalized symplectic structure, and we can furthermore integrate out this variation because everything will be linear in the fields. Now then there subsists a further residual ambiguity, but this, and this corresponds to adding a finite boundary term, but this can be fixed by demanding consistency with the subleading soft theorem. So at the end of the day, what we find is the soft charge for Virasoro and Diff-2 superrotation symmetry. So this is for a general diffeomorphism symmetry, but specified to these two Goldstone modes that I've discussed. I should note that while this expression was re-derived in harmonic gauge so that we can talk about these conformal primaries, it actually also agrees with previous results for Diff-2 symmetry in Bondi gauge. And it also agrees with the soft charge that was computed for Virasoro symmetry, where the contact terms have been dropped. So what happens here is that in this renormalization procedure, radially divergent contact terms and any other contact terms for this dimension 2 Goldstone mode get actually subtracted. And we are left with a function that is just holomorphic, 1 over z minus w to the 4. And this is all that remains in the soft charge for this dimension 2 shadow mode. On the other hand, for the dimension 0 primary, what happens is that the stuff that gets subtracted is some non-meromorphic function, while all that's left in the soft charge at the end of the day is given by a contact term. Now I can go back to the discussion of Virasoro versus Diff-2 superrotations. So what I've shown here is a superrotation symmetry for a particular vector field and the shadow superrotation symmetry for another particular vector field. And for this, we have found that these two symmetries are actually related by a shadow transform. Now, if we insist on having an equivalence between the subleading soft graviton theorem and the water density of an asymptotic symmetry, what this suggests is that perhaps we should include the closure of Virasoro under these shadows within Diff-2. On the other hand, if from the celestial CFT perspective, there exists an argument that says, for example, that we should exclude the shadow stress tensor, then our results would say that the whole asymptotic symmetry group just reduces to the Virasoro subgroup. Now, let me come back to these mode operators that I introduced earlier. So what I can say now is that in the conformally soft limit, where this mode operator has the dimension delta taken to 0, or a mode operator defined for the shadow primary with dimension 2, these two mode operators are related by a shadow transform for opposite helicity. These mode operators are radially divergent, just like the symplectic structure, but after renormalizing them, they are what is given by the soft charge for superrotation symmetry, for the Virasoro symmetry, and for this particular shadow superrotation symmetry in Diff-2. And up to a numerical factor, the renormalized mode operators correspond precisely to the stress tensor and its shadow. So from the point of view of the celestial, putative celestial CFT, these two symmetries appear to be on equal footing via the shadow transform. Now, this brings me to my conclusion. So I have described to you a unified treatment of conformally soft Goldstone modes of spontaneously broken asymptotic symmetries with a view towards flat space holography. Massless particles here are described by conformal primary wave functions, that have dimension delta and spin j under the SL2Z Lorentz group, which is the global conformal group on the celestial sphere. Finite energy wave functions are mapped to wave functions with conformal dimension on the principal continuous series. And the energetically soft limit gets replaced by the conformally soft limit, where the conformal dimension takes certain integer values. And I've explained that these conformally soft modes do not augment the basis, but instead can be obtained from certain contour integrals of principal series wave functions. Now, I've also discussed a symplectically paired set of zero modes, namely the dimension 1 Goldstone mode and the conformally soft graviton, which is the celestial version of the soft graviton, and how it was subtle to find this conformally soft graviton in the conformal basis. I have also given you an example for a celestial analog of quantum field theory soft theorems, namely the conformal soft graviton theorem. But there exists by now many other instances of conformal soft theorems for Young-Mills, for example, where similar factorization properties were recovered in this two-dimensional conformal basis. Now, these two tables summarize the conformal primaries and their conformally soft limits, which give rise to asymptotic symmetries and soft charges. I have focused on spin 2, but there's also a story for spin 1. So it turns out that when spin 1 conformal primary has its conformal dimension taken to 1, it reduces to a large gauge transformation. This is again not a trivial gauge transformation, but a large gauge transformation, and corresponds to a U1 Kac-Moody symmetry. The corresponding soft charge is given by the soft photon and soft gluon current. And there exists an analogous story for the shadow primary, but this coincides with the primary of dimension 1. Then for the spin 2 graviton mode, we found that for the limit where delta goes to 1, we recover BMS symmetry generated by the BMS supertranslation current. And then for the subleading soft graviton case, we have found this dimension 0 primary and its dimension 2 shadow. And Virasoro superrotation symmetry is generated by the stress tensor, while the shadow stress tensor generates a diffeomorphism shadow superrotation symmetry. Now, this was about asymptotic symmetries and how they manifest themselves in a two-dimensional language in terms of this conformal basis. This is one question that has to be addressed for understanding flat space holography, so whether asymptotically flat space is holographic, but there are many more questions to be answered. And I think we will hear more along these lines in the course of this conference. So let me just finish by saying that flat space holography is very much a developing story. And with this, let me thank you for your attention.
So thank you very much, Andrea. Thank you. So just a reminder to everyone, if you'd like to ask questions, please put your hand up. In the meantime, let me read out a question from somebody who doesn't have a microphone. So this is a question from Ecole Moll that everyone can see in the chat. And the question being asked is the following. So if you have a duality between a four-dimensional theory in Minkowski with a two-dimensional conformal field theory associated with a celestial sphere, it seems quite natural to think of generalizing the celestial sphere to a different compact Riemann surface with different genus. And really the questions are about that, you know, how would that work? What would the space-time picture would be? Would you still be able to have an asymptotically flat space-time? What would be the topology of the cuts of scry? So can you comment on that?
Yeah, so while it's not my own work, going to high dimensions, there have been works on extending each of those corners of this infrared triangle to high dimensions. So of course, we can study scattering amplitudes in high dimensions where we have soft limits. There exists work on looking at what are the asymptotic symmetries in high dimension as well as memory effects. For the space-time part, of course, this depends on what boundary conditions you choose. And then depending on whether you go to higher dimensional odd or even dimension, there exist some subtleties that have to be dealt with. But in principle, there's no obstruction to extending this picture to high dimensions. And of course, one would hope this to be the case, because at the end of the day, if you think that the UV theory is a string theory, there should be an embedding in high dimensions and also an embedding in string theory.
So just to say here, I think the question was not about going to higher dimensions. It was actually about taking a two-dimensional celestial sphere and replacing this
replacing
with a
that by a
compact
different
Riemann
dipole.
surface.
Okay. So yeah, well, the short question is, I have not studied that, or I have not thought about that.
My comment to that one would be, actually it's hard to get something which is asymptotically locally flat if you're using surfaces which are not of positive curvature. And so if you go to, if you start thinking of torus, the torus or higher genus Riemann surfaces, they're of course zero or negative curvature. And then you really struggle to make something asymptotically locally flat. So you might have to think about that. Okay, let me pass across to the first person who put his hand up, which was Andy Strominger.
Yeah, let me just comment on that last question. Sasha Zhiboidov and I wrote a paper maybe 4 years ago in which we talked about accelerating black holes that come out and puncture the celestial sphere and look like a sum over all operator insertions because their quantum states are correlated, and then sort of tied into a torus. And that, so the symmetrics might be a context in which you might hope to get something that looks like a celestial torus. That's an idea we've tried to make more precise and haven't succeeded, but there might be something there. My question for Andrea is there any context, any sense in which there is or have you computed a central term in the OPE of the stress tensor and the shadow stress tensor?
That's a good question. I cannot answer that yet.
You're trying.
Yeah, we're trying to understand what the appearance of this shadow stress tensor means, and whether the algebra has to be enlarged to the full BMS algebra with diffeomorphism symmetry. Naively would say that you have either the primaries or the shadows, but you should not include them both. So we're trying to understand how this also fits with this conformally soft mode that we found by including the shadow. So we're trying to understand what is the minimum sets of ingredients that we really need, and whether all the rest is extra redundant information since it's related by a shadow transform. But yeah, that's a very interesting question.
Okay, thank you. Next question is from Tarek.
Hey, Andrea, nice talk.
Hi, Tarek.
Yeah, sorry if this is a basic question, but just to ask you about this pairing between an operator and its shadow. So is what's going on there? So there are these things called supplementary series reps of the Lorentz group, and their inner product kind of looks like if you take an operator and its shadow and you integrate them. So am I supposed to think about it in that way in terms of the rep of the Lorentz group?
Well, this is a basic question, but that's why it's a difficult one. No, I have not studied these cross correlators yet. So they will for sure not be holomorphic like all the OPs with the stress tensor. But I don't know how to think of them yet in terms of more representation theory statements. But I will let you know as soon as we've computed them.
Thanks.
Thank you. There don't seem to be any more questions, so we thank Andrea again, and we will resume in about 10 minutes time for the final talk of the morning.